All right, let's get right into it. We're going to pull back the curtain on one of the most complex, high-stakes puzzles that gets solved every single second of every day, the power grid's ultimate balancing act.
Welcome to another video of Optatube. So glad you could join us.
Have you ever really stopped to think about it? It feels like magic, but it's not. There isn't some colossal battery somewhere storing up all the power. So how does the grid know, second by second, exactly how much electricity to make for all of us? Well, the answer is a fascinating process we're going to break down today.
In that process, it has a name, unit commitment. You can really think of it as the operational brain of the entire power grid. It's making thousands of critical decisions long before you even think about flipping that light switch.
So what is it exactly? Well, unit commitment is basically the master plan. It's this super complex job of deciding which power plants need to be on, when they need to be on, and exactly how much juice they should be pumping out. And it all boils down to two main goals: making sure the grid is totally reliable and doing it all at the lowest possible cost. To break it down, this whole thing really comes down to two big decisions. First, there's the commitment decision. Basically, which plants are we even going to use? On or off? Simple as that. Then you've got the dispatch decision. For all the plants that are on, how much power down to the megawatt should each one be producing?
Okay, so you might be thinking, just turn on the cheapest plants, right? Well, it's not that simple. Not even close. Grid operators are playing a game with a really strict set of rules. Rules that are based on hard physics and engineering. And these are the real-world constraints that make this whole thing such a massive challenge.
And rule number one, the big one, the one you can never break, is power balance. The total amount of power being generated has to perfectly equal the total amount being used. I'm not talking about every hour or even every minute. We're talking every single second. If that balance is off, even a little, blackouts. It is absolutely that critical.
Oh, and the rulebook doesn't stop there. Not by a long shot. See, every plant has its own limits, a minimum and a maximum power level. Then you've got these big plants, like coal plants, that have minimum up and down times. You can't just flick them on and off. Once you start one up, it might have to run for at least, say, 8 hours. Plus, they have what are called ramp rates. Think of it like a speed limit for how fast they can increase or decrease their power. And to top it all off, the power lines, the grid's highways, can get congested, just like a traffic jam during rush hour.
So what happens when things go wrong? Like a huge power plant suddenly goes offline, or there's an unexpected heat wave and everyone cranks up their AC. Well, that's where reserves come in. You've got spinning reserve, which is from power plants that are already running and connected to the grid. It's kind of like a car with the engine idling, just ready to go at a moment's notice. Then there's non-spinning reserve. That's from plants that are offline but can fire up super fast. Like a car in the garage that you know is going to start the second you turn the key.
Okay, so let's recap. We've got all these rules, right? We have to balance the grid perfectly, respect the physical limits of every single plant, and keep reserves on standby. It's a lot. Now let's throw in the other major goal here, winning the cost game. How in the world do operators figure out the absolute cheapest way to follow all those rules at the same time?
The goal is pretty straightforward on paper: minimize the total operating cost. But listen, that's not just about the cost of fuel. Nope. It also includes the cost to start a plant up or to shut it down. Literally every single decision has a dollar, or in this case, a euro sign attached to it. All right, let's make this a little more real. Let's try a simple puzzle. Imagine we need 200 megawatts of power, and we've got two options. Generator 1 is our cheap option at 30 euros per megawatt hour, but it can only give us 150 megawatts max. Generator 2 is pricier, but it's got more power to give. So what do? How would you solve it?
Okay, the smartest, most economical way to do this is to max out the cheapest option first. It's just common sense, right? So we're going to run generator 1 at its full 150 megawatts. But we still need another 50 to hit our 200 target. So what do? We have to turn to our more expensive generator 2, but only for that last little bit, just the 50 megawatts we need.
So you do the math. 150 megawatts at 30 euros, plus 50 megawatts at 40 euros, and the grand total for that hour is 7,500 euros. And that is the absolute cheapest way to get the job done with these two plants. Now, take that simple little puzzle and imagine doing it for thousands of generators for every single hour of the day, all while juggling every single one of those crazy rules we talked about. That, my friends, is unit commitment.
So, why should you care about the super technical puzzle? I mean, really, why does it matter? Because, and I am not exaggerating here, it is the invisible backbone of our entire modern world. It's the silent, constant process that keeps our lights on, keeps hospitals running, and keeps our whole digital life online.
All right, let's wrap this up with the key takeaways. First, unit commitment is a massive, massive optimization puzzle that gets solved every single day. It's this insane balancing act between meeting our electricity demand and following a whole web of physical and economic rules. At the end of the day, the goals sound simple, but it's incredibly hard. Keep the grid stable and affordable. That's the whole game.
So, if this is the kind of stuff that gets you excited, energy markets, power system modeling, getting the inside scoop on the global energy world, then you should definitely follow the Optatube YouTube channel. We'd love to have you.
And I want to leave you with one final thought. We've just walked through the traditional rules of this game, right? But what happens as we add more and more renewables like solar and wind? You can't just dispatch the sun or the wind on command. So the big question is, how do the rules of this entire puzzle have to change to keep up? That is the huge challenge for the future of our grid. Thanks so much for watching.